Welcome to Pod 4 Journal Club. Today, we're jumping into some seriously cool new research. It's about a new kind of AI model that could completely change how our machines understand, well, everything. So let's start with a problem we've all run into. You know, you're on Wikipedia and that one critical date is just missing. Or you ask your search engine a really specific question and it just totally misses the point. It's this universal problem of incomplete information. And for AI, it's a massive hurdle. So the big question is, how do we teach an AI to fill in those blanks? Not with wild guesses, but with facts that actually make sense together. To get our heads around this, we need to talk about something called a knowledge graph. Now, the easiest way to think about it is like a giant digital encyclopedia. It's the secret sauce behind a lot of the AI we use every day. Think Google search, think Amazon recommendations. But instead of paragraphs, it stores facts as these really simple three-part sentences called triples. Something like, Apple is a company. Head, relation, tail. Super clean, super simple for a machine to read. The only problem? These encyclopedias are full of holes. And that leads us right into the heart of the problem that this paper is trying to solve, all those missing facts. You see, real-world knowledge graphs are just naturally incomplete. I mean, there are way more facts in the universe than we could ever possibly write down. So what have we been doing to fix this up until now? Well, the older methods were kind of clumsy. They'd look at one potential new fact at a time, just one single triplet, and try to score it all by itself. But that has a huge fundamental flaw. It just doesn't see the bigger picture. It doesn't get that facts are all connected. And this leads to some truly ridiculous mistakes, like an AI predicting that someone is both the father and the mother of the same child. No good. And this image just nails the problem perfectly. The old way of doing things creates these logical nightmares, because every prediction is made in its own little bubble. It's like trying to put together a 1,000-piece jigsaw puzzle by looking at each piece one at a time, without ever checking to see if it actually fits with the others around it. It's just not going to work. We needed a better way. So along comes this new paper with a totally fresh approach. It's a brand new way to think about generating knowledge, and it leaves that old one-by-one method in the dust. The model is called DiffTSP. And its core idea is as powerful as it is simple: one pass generation. Instead of predicting facts one at a time, it tries to generate all the missing facts at once in a single unified go. This is a game changer because it forces the model to think about how all the facts relate to each other, making sure the final result is a consistent, coherent web of knowledge. Now, this diagram gives us a great bird's-eye view of how it works. It's based on a technique called diffusion. If you've seen those incredible AI-generated images from models like DALL-E, you're already familiar with the basic idea. The model essentially learns how to take a chaotic, messy, incomplete graph and patiently turn it into a clean, complete, and correct one. So, how does it pull that off? Well, it's this really cool two-step process. The first step is what the paper calls the forward process, but you can just think of it as making a mess on purpose. The AI takes a perfect graph of facts and starts adding noise. It systematically hides the connections, a little bit at a time, until all you have left is a jumble of disconnected points. It's kind of like taking a crystal clear photo and slowly blurring it out until it's just noise. And then comes the magic. Step 2, the reverse process, or cleaning it all up. This is where the real learning happens. The model is trained to perfectly undo the mess it just made. It looks at that noisy, blurry graph and learns to predict what the original clean connections were. Step by step, it removes the noise, restoring the graph until it's back in its complete, logical state. And the engine driving this whole cleanup operation, the brain, if you will, is a special kind of neural network called a structure-aware denoising network. Now, we don't need to get bogged down in the technical details, but what makes it so special is that it's designed to see both the tiny, local relationships between two facts and the big, long-range connections across the entire graph. It sees the trees and the forest all at the same time. Okay, so the theory sounds really elegant, right? But the question we always have to ask is, does it actually work? Let's take a look at how DiffTSP stacked up against the competition. So the researchers put their model through its paces on a few standard datasets. This table shows the results from a test on family relationships. Now, you can think of precision as accuracy, how many new facts were right, and recall is how much it found. But the number to really look at is the FTSP score. That's kind of the overall grade that balances both. And you can see right there, DiffTSP score of 0.635 is the clear winner. And this bar chart just makes it crystal clear. I mean, come on, that's not even a close race. It is a decisive victory for DiffTSP. That ability to generate everything at once, making sure it all fits together, gives it a massive advantage. And get this, it wasn't just a one-off win on a single data set. The paper shows that DiffTSP also hits state-of-the-art performance, I mean, the best of the best, on two way bigger and more complicated data sets from Wikipedia. This shows that the approach isn't just clever, it's also really robust and it can scale up. So, okay, the model works, and it works really, really well. But what does this actually mean for us, for the future of AI? Let's zoom out for a second and look at the bigger picture. Now, the authors are pretty upfront about what comes next. The first big hurdle is scaling this to handle the absolutely enormous web-scale knowledge graphs that the big tech companies use. They're also excited to see if this diffusion technique can work its magic on other kinds of complex data. And, of course, the eternal goal, making it all faster and more efficient. And this is why all this research really matters. This isn't just some abstract experiment. A breakthrough like this could lead directly to smarter search engines that give us way more accurate and complete answers. It could give our AI assistants a much deeper, more consistent grasp of how the world works. And it could create recommendation systems that suggest things based on a much richer, more human-like web of connections. At the end of the day, this is all about building an AI that can reason about the world more like we do, holistically, consistently. And it leaves us with a really fascinating question to chew on. If we had an AI that could reliably fill in the gaps in our collective knowledge, where would you point it first? What's the one area of human knowledge, from medicine to history, that you'd want an AI to complete for us? Let us know what you think in the comments below. And hey, if you found this breakdown interesting, be sure to subscribe for more from Pod 4 Journal Club. Thanks for watching.